We're going to be looking at this question, which is comparing the gravitational and electric fields. So electrostatic forces and gravitational forces can be both modeled by the idea of field, give one similarity and one difference between electric fields and gravitational fields. Okay, so for the similarity, you can write both obey the inverse square law, both the fields, and here we have the equation as well, which shows that they obey the inverse square law. Now, if you want to know a little bit more in detail, or you want to know all the possible answers to this type of question, I definitely suggest that you go to the playlist video. In that playlist video, I've actually included most of the points that they ask about these type of questions. Okay. So yeah, so both obey the inverse square law. Now I will include a few more points here as well. So they both have infinite ranges. You can write that as well. You can write that both of them are radial. Both the fields are radial. You can also write they both are an example of action at a distance. Okay, so those things that you can write. Now for difference, you can write that the gravitational field are for masses. Let me just write it properly. So the difference you can write is gravitational fields exert gravitational force on masses, but electric fields exert electric force on charges. You can also write other points such as that electric forces that act on charges are way stronger than the gravitational forces, given that they have the same separation. The charges and masses, they have the same separation. You can also write that gravitational fields are always attractive. Okay, and you can also write that the electric field can be attractive or it can be repulsive as well. So these are pretty much all of the type of answers that you can write. You can also write that the gravitational potential is always negative, and you can also write that the electric potential, it can be positive or it can be negative. So these are all the type of points that you can write. I prefer writing these two. This is for 2 marks. Let's move. Here we have another question. The graph shows how the gravitational field strength G of the Earth varies with distance r from the center of the Earth. And they've given you the values here. So they've given you the gravitational field on the y-axis, and then on the x-axis they have given you r, but in terms of the radius of Earth. So r is given in multiples of the radius of the Earth. Okay, so it's like 1 RE means 1 times the radius of Earth, 2 RE means 2 times the radius of Earth, and then so on it goes until 7. And then you have to show that G obeys the inverse square law. So we know the formula of gravitational field strength is going to be G is equals to Gm over R squared, where G is the gravitational field strength and R is the separation, or the distance from the center of one mass to the center of the other. So everything G is equals to K over R squared. So all you have to do is you have to do G times R squared is equals to K. And if you can show that for both things, that gives you a constant, which means that it obeys the inverse square law. So I'm going to pick two values out here. So let's pick this right over here, which is 1 RE, and that's going to be 9.8. Okay, this is the value, 9.8. So I'm going to pick 9.8 RE squared. Okay, and then let's pick another value from here. Let's pick 4 here, and then let's take this right over here, and we should get 0.6. Okay, so that's going to be equals to K, and then for the other point we selected, it was 0.6 times 4, was it 4 RE? Yeah, 4 RE squared. Okay, I think we did that, yeah, okay. And that's supposed to give me 16 RE squared, because 4 times 4 is 16. And when I multiply this two values, I'm going to get 9.6 RE squared, which is equals to K. So K is approximately same in both cases. 9.8 RE squared is approximately same as 9.6 RE squared. So K is equals to k. Both k is constant, so k is constant, and hence it obeys the inverse square law. A satellite is launched from the surface of Earth into an orbit height of 5 RE above the surface of the Earth. The change in gravitational potential energy of a mass when it experiences a vertical displacement can be calculated using this equation. Now we have to explain why this expression cannot be used to calculate the change in gravitational potential energy. Well, that's quite simple. It's because G is not constant, it's changing. When we use this equation, I've explained it, that G, we assume it to be 9.81 constant, but it isn't actually constant, so we can't use this, okay? Okay, now we have the final part, which says, calculate the change in gravitational potential energy of the satellite. So let's do this now. So we have the mass of Earth here, and the satellite goes from the surface of Earth to here, and it's going to be at a distance of 5 RE, and this and this distance here is RE. So it goes from RE to 5 RE. Okay, and now what we have to do is, we know the change in GPE is equals to M and then change in V. Okay, and then I know that the change in V is equals to the final position, the final potential minus the initial potential, and that's going to be GM minus GM over 5 RE minus GM RE. Okay, right. Then we can further simplify this minus GM over 5 RE plus GM over RE. Make sense? I'm going to take that GM out, so GM minus 1 over RE, 5 RE, plus 1 over RE. Okay? Then I'm going to take this, and I'm going to put it up there, paste. I'm going to move it right over here. Okay? And then this is supposed to be multiplied with M. Okay, this is the capital M, mass of the Earth, and this is the small m, mass of the satellite. So this is the mass of the satellite, mass of the Earth. Make sense? Now I'm going to put this right over here, multiplied. So GME MS minus 1 over 5 RE plus 1 over RE. Now all you have left is to just plug in the values and you will get the answer. And you're going to get the answer as 1.75 times 10 to the raised power of 11 joules.